approachability play roles in order for us to get the result. And this is a joint work with my great quarters, Rod from Chicago Booth, Joshua and Ashwin from Google Research, and my PhD student, Francisco Susan from MIT. Okay, so the main motivation behind this work is coming from many applications in modern online marketplaces. So think about like share economies, internet advertising, and cloud platforms. In all of these modern online marketplaces, there are real-time interaction between user and marketplaces. And because of these real-time interactions, these marketplaces can learn and optimize at the same time. But learning and optimization at the same time tend to be quite challenging because, first of all, we have future uncertainty. And then we also need to deal with time-varying environments as we are like learn and optimize at the same time. And more importantly, we need to deal with this computational complexity because in many like settings, the decision set for this optimization problem that marketplaces are facing is exponentially large. And then if one naively try to experiment with every single possible option, then we are going to have a very impractical algorithm. So then given these challenges, here's our high-level goal. We want to see if we can enable decision-making for modern online marketplaces by doing learning and optimization at the same time, despite having these three fundamental challenges. So here are like a couple of examples to make it like concrete and give you like some context what I mean by problems and optimization in modern online marketplaces. One is assortment planning. Assortment planning, in assortment planning, the goal is to decide what set of items you want to show to customers in order to maximize market share or revenue. And this is a problem that many companies face. Just think about Amazon. Every time you go on Amazon and search for something, Amazon needs to decide what set of items it want to show to on the first page. So another problem is product ranking. Think about platforms like Expedia. Again, every time you go there, like Expedia needs to decide how they want to display the products, in what order it wants to display the products, because there are a lot of empirical evidence out there that how things are being displayed greatly influence customer decisions. And as a result, it influences marketplaces, revenue, and market share. And last but not least, as another example that and another problem that marketplaces face, we have reserve price optimization in online advertising market, where the goal is to optimize personalized reserve prices for advertisers while we are selling ad views, we are running auctions. Okay, so now these are like some concrete examples. Now let's try to revisit these like three challenges for this application and see that if these challenges are actually real for them. So the first two challenges were future uncertainty and time-varying environments. So you can see that for assortment planning, demand is uncertain and time-varying. For product ranking, customer search behavior are uncertain and time-varying. Even if I'm looking at myself as a customer, I see that there's a lot of variation in my like personal shopping experiences. Sometimes I want to spend a lot of time like making decisions. Sometimes I try to make things quick. For reserve price optimization, what is like uncertain and time varying is going to be advertisers' valuation. But let's look at the third challenge, which is important. And the third challenge is because for many optimization problems, the decision set is exponentially large. So that's certainly the case for assortment planning. The number of assortments that one needs to try is exponentially large. And under some modeling assumption, you can write this problem as maximizing submodular function subject to some cardinality constraint, for example. For product ranking, the number of rankings that one needs to try is again exponentially large, exponential number of items. And again, under some modeling assumption, this problem is NP hard. You can write it as maximizing sequential submodular function. And for reserve price optimization, the same thing, you have the NP hardness result for that problem.
Can I ask a naive question? So for example, in the product ranking, like what you show up where, what are you trying to optimize?
So you could have like different objectives. So one objective could be like maximizing consumer engagement, which is the probability that you get the maximum number of clicks from the customer. You could have, if in case like you're getting commission, you're selling things like Expedia, maybe you try to maximize your revenue. So you can have like various objective depending on the platform. So for like social media platform, a good maybe objective is customer engagement, maximizing customer engagement. But for platforms like maybe Amazon, maybe maximizing revenue would make more sense.
Revenue for Amazon.
For Amazon, maybe maximizing revenue makes more sense. Or they may have like, if they think about like their long-term goals, they can also try to maximize their market share, which is equivalent to maximizing consumer engagement.
It'd be hard, so in the worst case, if you impose some restrictions, it might become a simpler problem.
NP hardness is for the worst case, yes, but yeah, so this problem is hard because of the combinatorial natures. That's it. Any other questions? Okay, so then what we are going to do for all these problems, we want to learn and do the optimization at the same time. And in the rest of the talk, what I'm going to do, I'm just going to focus on this problem, assortment planning to maximize market share, as the running example to illustrate our technique. Okay, so for those of you that you are not familiar with assortment planning, bear with me. It's just what I'm going to describe is simple optimization problem. And so then if you learn that, if you are okay with that optimization problem, you can follow the rest of the talk. So in assortment planning, we have n products, and then the goal is to choose a set or assortment S with cardinality at most K that maximizes market share, where the market share is the probability that one of the item, at least one of the item within the set is being purchased or is being chosen. So this F function, I'm going to refer to it as a market share or demand function. So what you want to kind of know about this problem is that under various choice model list F is monotone and submodular. Okay? And that's the only thing I want you to remember from that problem. So now let's think about the offline version of that problem when we do the optimization. Over there, I know this F function, this demand function, and my goal is to choose set S star that maximizes this demand function subject to cardinality constraint. And this problem has shown to be NP hard. And that's related to the third challenge that I was talking about, having like computational complexity.
So is it important to exactly understand the definition of F? Or is it enough to know it's a monotone submodular function?
So for now, let's say that I don't care about its definition. It could be like any submodular maximization, submodular monotone function. Because for like various choice model, like mixed amenable and nested logic model, all of these things, this F is monotone and submodular. And that's the only thing we care about. So the form doesn't matter. That's a good question.
And the S can be any set or there are visibility constraints.
So here, like S can be any set. The only constraint that I have is the cardinality. But this is just a running example to illustrate. Okay. So now let's look at the online learning problem, because remember, I do care about this real-time interaction between the platforms and users. So in the online learning problem, every round T, there's an unknown demand function, f of T. I don't get to observe f of T. Without observing that, I have to make a choice. I need to choose set SD. After choosing that set SD, I get to observe some information. It could be in this full information feedback structure when you get to observe the entire demand function, or you could be in the bandit feedback structure that you get f of T at the chosen set ST. We study both of them. We have results for both, but mainly in today's talk, I'm just going to focus on the full information set. Yes, Daniel.
FT is a probability, right?
So it's a set function.
So FT of ST rather, how would you observe FT of ST?
Is a probability.
So how would you, you just observe 1 or 0? How would you observe the actual probability?
Oh, good question. I think right now, let's assume that I do observe the probability, but it's not very difficult to also consider saying that you only observe the realization. So yeah, but for now, let's assume that I get to observe the probability by having let's say showing that thing to the multiple user, and then that's a good question. And the benchmark is in hindsight optimal, where in hindsight optimal, I need to choose a single set that maximizes the total market share across all the tiers. So, and then in the online learning problem, that's what we are competing against. This is the in hindsight optimal that we are competing against. Okay, now let's actually see what we want to do here. Remember that I said I want to facilitate learning and optimization at the same time. So that means that at a very high level, I want to go from offline optimization to the online learning regime. Because the reason that we are going to do that is that in many cases, when you look at the offline problem, we have a very good, despite having this combinatorial challenge, there exists some approximation algorithm that gives us good performance guarantee. So think about greedy type algorithm, primal dual technique, or like LP relaxation, you name it. And these type of algorithms have a good performance guarantee, but those guarantees only hold in the offline regime, not in the online version. But we want to understand if we can get a similar guarantee for the online regime when we have real-time interaction between users and the marketplace. Okay, so have that question in mind. So here's what we are going to do. I'm going to develop a generic tool to transform these offline algorithms that are designed for only offline regime, and then somehow transform them to online algorithms with a similar performance guarantee. And by similar, I mean those when I do the transformation, their online convenience is going to get similar performance with no performance loss when you look at things over time. And now, if I want to become more concrete, the way we are going to do that is that we are going to mimic the structure of this optimal, this offline approximation algorithm using Blackwell approachability. And that's where Blackwell approachability plays a crucial role. And you may wonder, why do I even want to mimic the offline approximation algorithm? The reason you think that mimicking is a good idea is that these offline approximation algorithms tend to exploit the combinatorial structure of the problem. And when they do that, they remove the necessity of evaluating this combinatorial function at every single option. Okay. And without doing such a extensive evaluation, they manage to return something which is near optimal. Now, if I do this, if I try to mimic this approximation algorithm in the online regime, I can also exploit the combinatorial structure in a very implicit way. And by doing that, I can remove the necessity of experimenting with every single option. Okay? And that's why I think at the very high level, mimicking this structure of the offline approximation algorithm is a good idea. And it's become more clear later what I mean by mimicking. But for now, this is at the very high level. Because of the combinatorial structure, I want to mimic something that has already taken advantage of the combinatorial structure. Any question? Before I get to details. Okay, so perfect. And in this work, what I'm going to do is that when it comes to this mimicking or transforming these offline approximation algorithms, I'm going to focus on a large class of problems that admit greedy type algorithms. Okay, so their offline problem admits a very nice greedy type algorithms that has a very nice theoretical guarantee. This is the case for assortment planning, for product ranking, and for reserve price optimization. For all of these problems, there exists very nice greedy algorithms that gives us good approximation factor. And we are going to do the transformation. We are going to do the transformation for this type of algorithms. Okay, so if the focus is on greedy algorithms, let me walk you through the greedy algorithm for our running example, maximizing submodular function subject to cardinality constraint. And many of you may know this algorithm. This is a very elegant algorithm. It's a kind of classical algorithm by Namhasar et al. It's an algorithm that gives 1 minus 1 over E, and this is designed for maximizing any submodular, monotone submodular function. How does it work? You go over case subproblems. In subproblem I, you choose element Zi or product Zi that maximizes the marginal market share delta F. And then you add that product to your set. You keep doing that until going over all K subproblems. Remember, K was the cardinality. And then you return S of K as your finals. Okay, so this is the algorithm, the greedy algorithm. And you can envision this greedy algorithm in the following way. So there are K subproblems, subproblem I, choose Zi. And then choosing Zi, you can think about it as finding the best local move for that subproblem. And then you find this best local move by going over this case of problem. You can get a solution which is really good. It gives you 1 minus 1 over the approximation, which is the best approximation factor for that problem. Okay. Now, the question that we ask ourselves is that, is it possible to transform this offline greedy-like algorithm in polynomial time to their online covariance that gets sublinear approximately? So first thing, what is approximate regret? So approximate regret is a regret where you measure your performance with respect to gamma times the in hindsight optimal, where gamma is the approximation factor of the greedy algorithm. And this is what the algorithm gets. This is going to be gamma times the opt-in hindsight, the benchmark. And you may wonder, why am I actually putting gamma here? Why not like calculating regret instead of going with the approximate regret? The reason is that the online problem is definitely much more difficult than the offline version. And for the offline version, I'm not getting better than gamma approximation. So the best thing that I'm hoping to do is getting a sublinear regret with respect to gamma times opt-in. And if I do that, so then I can say that's a good result, because pretty much I get like similar performance in the online regime without knowing all this like reward function over there. Okay. So now I think like after that, things getting like quite nice, because now actually I can get to show you the elegance of Blackwell approachability and how it plays a role in our transformation. So what I'm going to do in the rest of the talk, I'm going to provide you like a framework. That framework needs two generic conditions. One is related to Blackwell approachability. And then I show you that under these two generic conditions, you can do this transformation, get a sublinear gamma regret, and for the online regime. And then I'm going to also show you that for a large class of problems that admit greedy type algorithms, these two conditions are simply satisfied. That's where we are heading. So now here are the two conditions. The first condition is called robustness of greedy algorithm to local errors. So remember that in the greedy algorithm, I'm going over a case of problems to build a solution. Now imagine that in every sub-problem, instead of doing my local task optimally, I do it with a little bit of mistakes, a little bit of error. Under this robustness condition, I want the error across different sub-problems don't get propagated, don't get amplified. I just want the error simply add up together, or even like get aggregated in a sublinear fashion. That's what I mean by robustness condition. Now the second condition is Blackwell locality. This Blackwell locality condition requires that every subproblem I that I have to be, can be cast as a Blackwell game. And I'm really glad that I'm giving this talk after the nice talk by Rakesh, because right now you have like some idea, some good idea about what the Blackwell game is. But I'm still gonna like give you, refresh your memory, but and then later tell you why these two conditions are actually nice to have and gives us the result that we want. Okay. So let's get to the provide some information about this Blackwell game. You've seen it in Rakesh talks as well. Yes.
A question about the first condition. So is the error in the function itself a payoff, or is it an error in I'm choosing the wrong action and somehow that doesn't matter?
So let's say that the best local move is returning an item that has the maximum margin, right? This is your local move. Now, let's say that I'm returning a distribution over products, and then I want the expected marginals to be maximized. This is kind of equivalent to doing this local move optimally. Let's say instead of finding this local move optimally, like exactly returning the item that maximizes the marginal, I give you some distribution over products such that the expected marginal market share is still not too far from the maximum thing that you don't know. And that's what I mean by error. And if you make an error in making this the local move, I want the error overall in terms of the final things that you are getting, this f of t at the chosen set to be small. Any other question? Thank you, Ali, for the question. Okay, so now what's the Blackwell game? Because for our transformation is quite crucial. Let's look at this repeated Blackwell games. And then repeated Blackwell games, I have like two players, P1 and P2. And it is a zero-sum game. And then the important things, as Rakesh mentioned, is that in this game, the payoff is a vector. And it's also more importantly, the payoff should be by affine. By affine in the decision made by the two players. So in every round T, player P1 is going to choose an action XT, player P2 is going to choose an action YT. Then after that, P1 obtains the payoff at the chosen actions, and then P2 gets a negative of that. And that's what is a zero-sum game. And this process like continues. So now, what is the game? The P1 wants to approach a convex set, and P2 does not want this to happen. And when I'm saying approaching this convex set is saying that the distance between this time average payoff that P1 gets and this convex set S goes to 0 as T goes to infinity. So that's the thing that the P1 wants to achieve. Now, the very elegant result by Blackwell shows that if set S is approachable in terms of like hyperplane approachability that Rakesh mentioned, which is a very easy thing to check because you need to check something only in a single shot Blackwell game rather than in a repeated setting, then there exists a strategy for P1 in the repeated game that no matter what P2 does, P1 can actually approach that target convex. And very amazingly, like when you look at the proof of the Blackwell approachability, the proof also tells you what is the strategy that P1 needs to use in order to approach these targets. Not only tells you that the P1 can approach that target set, it also tells you how, with the help of what algorithm this approachability is possible. So what I want you to remember from this slide is that if set S is well behaved, then there is an Blackwell algorithm ALGB that helps P1 to target the convex set. So that's the only thing I want you to remember. Now let's try to put these two conditions together, and let me tell you why this is kind of based on these two conditions. I can manage to transform offline algorithms to their online counterparts. So remember that we had this Blackwell locality that wants us to cast every subproblem I as a Blackwell game, which means that I need to come up with two imaginary players, come up with some by affine payoff vector that are and some like approachable target convex set. Then once this happens, I would say, okay, here is like an ALGB Blackwell algorithm that is going to help this player P1 to generate a sequence of actions that maybe they are not locally best, but they're almost locally best when you look at things in average over time. Okay. So here's what we are going to do. Subproblem 1 is going to be handled by Blackwell algorithm ALGB1. ALGB1 is going to decide about the first product that we are going to add to the set. It's going to pass this decision to another Blackwell algorithm. The other Blackwell algorithm make a decision about the second product. And this whole thing is continue until going over this case subproblem. Okay? And the reason I can handle this every subproblem with a Blackwell game it's because of the Blackwell locality condition. And then what about the second condition? What about robustness to local errors? So the robustness to local errors is actually quite nice because it allows me to glue everything together. But I don't care about like each of these subproblems separately. I do care about the final product after going over all these case subproblems. So robustness to local errors allow me to make sure that when every subproblem is being handled by Blackwell with some error, let's say in the order of a square root t, then overall after going over k subproblems, the final like error or the regret is going to be k times that, which is going to be k times a square root t, roughly speaking. Any question about the high level idea before I move on? I'm going to like revisit these high level ideas later, but I want to see if there is any question about the.
So you're going to have k different Blackwell games
Yes.
that are played every round.
They are going to like at least for that problem they are working in a sequential fashion, but yeah, in every round there are k Blackwell algorithms. Each of them are responsible for.
So then like my action is tied across these k. Like I can't pick a different action for each game, or can I?
No, like let's say that Blackwell algorithm 1 decide about item 1. So then item 1 condition on this like item being chosen. Blackwell algorithm 2 like decide about the second item it wants to add to that set. So they are this is actually very nice. These Blackwell algorithms communicate with each other. It's not like they are not being run in parallel. So, and in other words, they're mimicking the structure of the greedy algorithm. So this makes a decision, passes decision to the next one, and based on that, the next one makes a decision. Thank you, Nico, for the question. Please.
Isn't the robustness assumption restrictive? Because I think the greedy may take suboptimal decisions that affect in long term.
So good question. I think this robustness condition, first of all, is important for us because if you do each of these tasks like almost well, doesn't may not mean that overall you are going to get a good solution. And there are some greedy type algorithms that are not locally robust. But as I was actually going to tell you that, and you are ahead of me, for all this like problem that I talked about, assortment planning, product ranking, and result price optimization, we have the robustness condition. So there are like various problems that this condition can be satisfied, but not this condition may not be always satisfied. Thank you.
So other than
Yes.
the robustness property and the fact that you have a natural split of your problem nature into some fixed number of subproblems, how else would you be using sort of like that if you're working with the greedy algorithms?
That's the only thing. If you give me a greedy algorithm and I can like break it down into like multiple subproblems, then if I can show that every like small task, every subproblem can be cast as a Blackwell game, and then you have the robustness, then you cannot follow up from. That's other than that, I don't need anything. Okay, so no, I think in terms of the contribution, as I explained, so here in this work, we design an efficient framework to go from offline to online setting. And our transformation crucially uses Blackwell approachability, and it needs these two conditions: robustness to local errors and Blackwell locality. And for any like problem, as long as you satisfy these two conditions, you get a square root T regret for the full information setting and T to the power of 2/3 regret for the bandit setting. And when we came up with this like framework, we were quite excited because we applied to a wide range of application in operation and markets. And as you can see here, in all of these applications, we managed to show that these conditions are satisfied. And then when we applied, we either got the first bounds for these problems, or like matches the best known bound in the literature, or even like improve them. So here, for example, we applied to product ranking, result price optimization, various submodular optimization problem, continuous and discrete, and subject to various constraints. So you will see that for full information setting, we get a square root T dependency. For the bandit setting, when the decision set is discrete, we get T to the power of 2/3. And when the decision set become like continuous, because of the discretization error, the regret is either T to the power of 4/5 or T to the power of 5/6. And another thing that we find it quite exciting is that when you look at this result for the bandit setting in the prior work, although the bandit setting is very realistic, and it's kind of like what's happening in what you would need to have like a practical algorithm, you will see this column is quite sparse prior to that work, and we were excited to contribute to the literature by providing the first bounds for the bandit setting for various problems. Okay, so I know that today we are going to talk about Blackwell approachability, but in case you are also like kind of like wondering what is the literature about this offline to online transformation, maybe I can make a few remarks about that. So first thing is that you cannot always do this offline to online transformation. Okay? So there are like negative results in the literature that for some combinatorial problems, it's not actually possible to do that. That's a nice result by Hassan and Koran 2016. The other thing that I want to mention about this offline to online transformation, usually prior work take a black box approach, meaning that they assume that there's an oracle for the offline setting that you can call, and then based on that, you decide like how to actually make a decision in online setting. So we don't take a black box reduction approach, and we actually do care about what's happening inside the offline algorithm, and we take advantage of the structure of this offline approximation algorithm. So, and speaking of this black box reduction, there are nice paper by Kalov and Paulo 2005 and Dudik et al 2017. Nico actually has a nice paper on that they do this offline to online transformation, but for them, when they need the oracle for the offline problem to be exact, which is not the case for us because we are dealing for NP-hard problems. And then there's also this nice work by Kakade et al. 2019. They also take the black box reduction approach, but for approach, it's crucial to have linear reward, which is not again the case for us. Even for assortment planning that I discussed, we don't have linearity. And that's why like prior works cannot be applied to our setting. So the bottom line is that in this work, we look at this NP-hard problem with nonlinear reward structure, and we use the like elegance and magic of Blackwell approachability to do the transformation from offline to online. And we got result for both full information and bandit setting. So any question before I move on to more details? So then if there is no question, let me, as I promised, I'm going to provide you high-level sketch of our approach. And because this day is actually dedicated to Blackwell, I just want to show you how is it actually possible to cast our sub-problem as a Blackwell game, and how this help us like to get the result that we want. So remember, at the very like high level, we wanted to mimic the greedy algorithm. This is what we wanted to do when we wanted to go from offline to online. And then that means that every like run, I want to go over these like case sub problems to make a decision, kind of roughly speaking. So if that's what we are going to do, maybe here is like one idea. What if for like every sub problem I, like for example in run T, I choose product ZI that maximizes this marginal, okay? Can I actually do that? Meaning that can I make this best local move? The answer is unfortunately no, because you don't have the knowledge of f of t when you are making that decision. So then you cannot really mimic this greedy algorithm in this way, in this like naive approach. So instead what we say, what if I try to look at these sub problems across all the T runs and say that let's make sure that every sub problem I make a sequence of actions that are almost locally best, but on average sense over time. Then maybe that by doing that, we were able to kind of mimic the structure of the greedy algorithm. And in fact, this is possible under this Blackwell locality condition. Under Blackwell locality condition, I can just focus on this sub-problem across T runs and then create a sequence of action that are almost locally best when I'm looking at things over time. So let's actually revisit the greedy algorithm to provide more information about how this Blackwell locality condition is satisfied and how I can cast it as a Blackwell game. Remember that in subproblem I, I'm choosing a product ZI that maximizes the marginal market share. Okay, so then choosing a ZI that maximizes market share is equivalent to say that this payoff vector, which is a vector actually, is greater than or equal to 0. So let me parse it for you. So this is the marginal under product ZI, this is the marginal under product 1. So if ZI is the one that maximizes marginal, of course, this difference should be positive. Okay, and that's the same thing for all the other coordinates. So now I saying that ZI maximizes the marginal is equivalent to say that this payoff is positive, is in the positive order. And there's the issue because if I want to cast this as a Blackwell game, I don't see the linearity in ZI. And actually for Blackwell, it's crucial that the vector payoff to be by affine, and I don't have it. So I'm going to massage this a little bit, not a very fancy trick, but it's going to help me. So let's assume that the greedy chooses distribution over products rather than returning a product. And then I can write payoff in terms of this distribution theta I. And that's without loss of generality, because if I have a product that maximizes marginal, then I can say that I put a mass of 1 on that particular product. So then this yellow thing that you see here is just simply the expected value of marginal market share at the greedy decision. And now what I did, this is again, you can see that this payoff should be positive. But the very nice thing is that this payoff is now linear in theta I, which is what I wanted to achieve. Okay, so here is the part which is kind of, I think, explain how this Blackwell approach will help us and we can cast it as a Blackwell game. So my imaginary player P1 is the algorithm that decides about theta I. My imaginary P2 is a nature that chooses this delta F. The payoff that I have is again the same payoff that I show you. Is a vector, is definitely by affine in theta I and delta f. So everything is nice. And also the target set, what actually P1 wants to achieve is that this payoff to be positive, because if payoff is positive, that means that I choose the item that maximizes the marginal. So that means that the target set is simply the positive one. And it's easy to see that it's approachable. Yes.
So detailed clarification. This SI minus 1 is actually a function of t, and this doesn't create problem.
No, it doesn't create any problem. And then here I'm just to make sure that something like a subproblem I can be cast as a Blackwell game, you need to only looking at the single shot Blackwell, single shot Blackwell game. So, and that's another nice thing because checking the condition is very easy. And then yeah, it doesn't matter that's a function of t. So now I define everything I wanted. Two imaginary players, a payoff vector which is by affine, a target set which is convex and approachable. And then I show that you can cast it as a Blackwell game. And if that's the case, there is a strategy, this Blackwell strategy that help player P1, which is our algorithm for that subproblem 1, to actually approach this set, meaning that makes the almost locally optimal move for that particular subproblem. And again, like here, I just revisit the high level ideas. Because of the Blackwell locality, I can handle every subproblem I with a Blackwell game. And that's, and then after that, they pass the information, make a decision. And because of the robustness error, the outcome is going to be still has a nice property because the error does not get amplified. So, so I try like, and then we get this full information, like we get this theorem under full information setting, which is as long as you have the robustness to local condition, to local errors, and you are Blackwell local, you can go from offline to online and then get the regret, which is in the order of k square root t, where k is the number of subproblems. Yes, sir.
What information is transferred between the subproblems? So at the beginning of every round, how the subproblems.
Okay, so yes, the question is that how do I like what's the information structure? So let's say the subproblem will make a decision. And then after that, the only thing I need to pass the subproblem to is the item chosen. And then after like subproblem 1 and subproblem 2 make a decision about item 1, product 1 and product 2, I need to just pass that set to the next Blackwell algorithm. Just literally following what the greedy algorithm does in the offline setting. So that's the information. And then for the full information setting, after I make all this decision, I get to observe the entire function, the f of t. And then I pass that to the Blackwell algorithm so that they can update themselves. For the bandit setting, it's become more complicated because I only get one piece of information. And then the question is that to which of them I want to handle, like I want to pass that information. We handle that, but for the full information setting, you can just pass that information to each other. Thank you. Yes.
Let's see about VDL one that makes it. Let's say I was doing dynamic programming with a contract state.
So actually, very good question. I think like we are actually working on that. We believe that for like a dynamic programming type algorithm, you can still follow the same thing as long as there is no loop in the structure of the algorithm. You can do that. So let's say that you can represent the algorithm in form of like a DAG, and then you have like a small number of states. In your like dynamic programming algorithm, you can still apply that under like some condition. You have some like partial result that you can do it, for example, for knapsack, for the DP for design for knapsack. And you can also apply it to Frankfurt type of algorithm. So there is nothing like special about greedy as long as you can satisfy robustness to local errors as well as the Blackwell locality condition. As long as you can check that, you can, and then there is no loop in the system, like a cycle in the system. So then you can apply this technique. So it's very powerful and flexible. Yes.
Quick question. So this robustness to local errors, is this basically a property of Nemhauser's algorithm that we use?
Exactly. So it's a property of the offline algorithm, and that's what I mean that we are not doing the black box reduction. I actually care about what does the greedy algorithm does. I need to kind of take a closer look, zoom in and see that it is property in the offline algorithm what makes sense. Yes.
In terms of extending this to other algorithms, is it important that it's incremental, that the rewards get added up along the sequence of
good
like TP is?
Yeah, I think as I like, it's kind of related to the question that Shipra asked. As long as you don't need to like to have a chain like that, you can have things like that are completely parallel. You can also have things that in form of a DAG, so that things like passes along multiple passes along multiple passes. So then that also could work as go.
And another question: the dependency on K here is linear. Is it? Do you think it interesting? Future work to kind of try to shape some.
Very nice. I think like for this submodular optimization, it's linear, but actually when we are looking at maximizing continuous submodular function subject to downward close convex set, we show that this robustness condition is even like better, like meaning that the error gets aggregated in a sublinear fashion. So we improve the K to something else, and that's why we managed to get to the power of 5, 6.
Because for noisy submodular maximization, you would already have that K with randomness.
So let me try to be quick. So there may be, we did also some simulation because we're excited to see how this algorithm performs. One very nice thing is that we observed this cumulative gamma regret are actually negative, which was surprising. We first like checked the code if something wrong, but then we realized that there is nothing wrong. The reason that even like the regret is negative is that we are like mimicking these greedy algorithms, and greedy algorithms, in the worst case, they get 1 - 1 over E or like this gamma approximation. In practice, they do much better, and we mimic them. So that's why that in practice, by mimicking them, you get like even negative regret, negative approximate regret. Okay, so let me summarize. So with today, as I said, it was an honor to talk in a day dedicated to Blackwell, because at the gist of our approach, we crucially use the magic of Blackwell approachability to do the transformation from offline to online. And using this transformation, we get a square root T regret for the full information setting and to the power of 2/3 regret for a bandit setting. And one thing we at least find quite amazing was the flexibility of the framework and the fact that can be applied to various problems, including product ranking, reserve price optimization, and several submodular maximization. Yeah, thank you so much. So thank you for listening to my talk, question, and there's a link to the paper, my email, and I will take any question that you might have. Thank you.
To make a brief attempt to get back a little closer to schedule after the break, I think let's take questions offline and let's take a shorter than expected break. Do you want to come back at 11:10, Sid, or 11:05? Sid says 11:05, not my fault. 5 minutes, 5-minute break. See you soon.